Test. Works. So man, you ready for present?
So much so. What?
What was your topic?
What? I don't know what it is.
Is it?
Yeah, like it's in the YouTube video. Of like, you know.
We did.
I did it, so I like send it to him and he had to fix the code for me.
Really?
Yeah.
I didn't forget any of what I was doing. Mine is actually 4 slides. It would have only been 3, but he wanted me to do this, or he wanted me to increase the momentum values. But I just did it into ones I wanted to do. So
Yeah. Mine's like 8, but I don't have a ton of information on each slide. Oh, last.
exactly. Oh, yeah, this view. So, yeah, I need to represent this photo somehow.
Shows earlier. Maybe that I expect first place.
We need to start time for this class.
11.
Okay.
You sent me this one. You did. But sharing
Take your feedback.
Yeah.
What do you say?
He told me to add some stuff, but then he already downloaded.
This represents. It's like a particle, right?
I remember when we did the thing where we were with the parts together to get like the product of the particle for the partition.
I think there's more than one. I don't know.
This isn't it like, oh no, there's one that stands still and then there's one that's. So
Yeah.
I don't know what that is.
I know, and I think I'm supposed to know. Like it's not really my topic, but kind of is my topic. So I feel like this is probability on the y-axis, right? And this is like position. And then it's like it's an oscillator, isn't it? Because it's going back and forth.
That makes sense.
I don't know why there's 2. It's probably two particles. I don't know. I might have to look at the code.
It would make sense that it would be 2 particles, because one is standing or one is sitting still, and the other one's oscillating. Back and
I
forth.
might have to draw something on the board for mine because I completely forgot a slide. Well, like this is what I did. I did like it's like this is what I thought this, but this is Ifeanyi's. This is Ifeanyi's slide part of this thing too. Okay, this part is, but everything else, this is mine though. All 3 of these. I just forgot one part, so after this one, I'm gonna have to draw something to explain it. Be like, this is the probability of like a wave.
See, I feel like I understand my topic, but then at the same time, I just don't. Like he's at an international conference right now or whatever.
And we're
He said
still
he's-
presenting.
Yeah, he said he'll pop in and out if he can.
We're presenting by that guy.
Yep. Yep. Yep, he's gonna have it
Is
recorded.
Is it?
He's gonna have it. Yep. It's no microphone. Yeah, so we're presenting in front of him.
For the analytical lab, you see it like a 0.14 something, right? For the KMNO4.
I got 0.03, so yeah.
Well, I haven't started that.
And then I
I'll
also
wait till
got
Sunday.
48.9% calcium.
I had like a
Represented as calcium.
0.14 concentration.
Did you even put my third lab in or the
It's
grid?
still not quite what it's supposed to be.
You said 0.1?
Yeah.
I thought it was supposed to be 0.02.
Shoot, really?
Yeah.
I hate that picture.
Yeah,
Maybe I
then
calculated it
Then
wrong,
like the
though.
last step says titrate with 0.02 mole.
At least ours looks
or
normal, you have
manganese.
Spencer's, it looks like a
So I think we were preparing a
Yeah,
0.02.
how did we get that
I just
picture?
converted the oxalate to moles, converted like mole
Student,
of
I mean-
oxalate
Oh.
to manganese, which is like 2 to 5.
Yep.
And then I divided by the volume that we added for the hydration, which is like 0.02.
So, yeah, I think I just wrote it down here. So convert it into moles, use the relationship, and then just divide it by the volume. And then it gets 0.236.
But yeah, I did take the calculation the same way.
What did you get for a volume?
Like 0.02917.
Oh, damn.
That's right,
That's
yeah.
a bigger number than we got.
Oh, I think that's probably why then we have a difference. For the final calculation, are we converting like the KML4 to a ratio of like this calcium oxide?
Yeah, so I just used the volume that we used to titrate the calcium oxalate. Use the concentration of the remaining solution and then use the ratio. There's another ratio to get the calcium oxide, and then I use the molar mass of the calcium oxide to get the total. So then it ends up to be 0.9%. Interesting.
I wonder what it's supposed to be.
I was looking some stuff up and it looked like about half. That's like a.
So yeah, it makes sense.
See if I can correct Jackie heard. She heard that means that I have conclusion last time in the discussion. Grades are live reports.
So you're shouting.
It's like in the discussion, I have the equations and she says no one should be in the introduction.
Because you're supposed to talk about the equations in the introduction.
But
I mean, it makes more sense if it's in the introduction, but because then you can recall back to it in the discussion.
how it's in discussion.
No, it recalls back to the things that are in the introduction. Equations are.
It's pretty traditional from
First, but it's just the one we get the template hasn't been discussion, not the introduction.
Well, just put it in the introduction. It makes more sense if it's in the introduction.
Yeah, I know, I'm just.
That's how I've always.
How are you? Very good. This room still feels like a plaza. No way.
Sure, it's not a room. Very useful.
Apparently there's 9 presentations, so a lot.
And this part is just.
Oh, God, I'm having publications.
So I forgot one again.
So there and talk about it, brought it.
That's fine, so
Like,
I don't discuss any of my actual methods now. Here's your.
Anna, at least you guys are smiling in those pictures.
I'm very flattering too. Oh, gee.
And do you see what I did?
Oh. Kyden is attending some international conference
Okay.
and he's giving a talk on carbon nanotubes
Okay.
online through Zoom. So I guess I need to be the temporary host for
Okay.
at least 30 minutes. I guess he will be back in 11:30.
Okay,
Yeah. So I guess maybe we can get started.
Don't judge our presentation.
Yeah.
Yeah.
Set your expectations.
So here are some graduate students. David is from Dr. Kinney's group and Steven from Dr. Kinney's group. So I guess, so basically we have 9 presentations and each one will be 5 minutes, including questions. So let's invite our first speaker, James. Is James here?
He's probably be here in another 5 minutes. James, I think of you running.
Do you want to wait or do you want me to go?
Or maybe you can go.
Okay.
Thank you. No, that's. Meeting minds, yeah.
Do that.
Well, this is my third presentation of this class. All right, I'm going to be talking about the commutation of operators in a numerically expressed, and the conversion of operators between position and momentum. Oh. Do I just keep going? Just keep doing it, okay. All right, so traditionally, an important characteristic of operators is that their order in which they're applied to the wave function matters. So A applied first and then B applied to the same wave function does not equal B applied first and then A. But if they are, the order does not matter, so they equal each other. In quantum mechanics, position and momentum operators are not commutative. This relationship gives meaning to the Heisenberg uncertainty principle, which means like the more certain you are of the position, the more uncertain you are about the momentum. That just kind of reiterates that. So if we're calculating the commutation relationship between position and momentum, we define the position operator as x, and the momentum operator as negative I h bar. So if we apply these and take the difference of their products, we get negative h bar. I don't know if you want me to go through the computation. And so this describes it in 1D. So how can we describe it in other dimensions? We redefine our position operator as this, and then instead of the partial in our momentum operator, we use the gradient. And so if we apply these, and then we find the difference of their products again, we get switch side of our relationship. So we had negative IH bar, and now we have positive. So the I component of our relationship defines this as imaginary. What does this look like in MATLAB, you might ask? Our position operator is only represented as the diagonal elements of matrix, and then our momentum operator is diagonal, but it also contains negative numbers to account for the wave function having negative momenta. So what does our commutator look like in MATLAB? Well, in one dimension, we have our negative sign, and it looks like that. So in conclusion, this expects what we would, no, this looks how we would expect it to. Thank you.
Question from audience.
When you were solving for the commutator relationship and you gave an example of for position and momentum, how would you gave the values of the operators, but would you have to act them on a wave function to actually solve this?
I don't believe so. I can't give you a good answer.
The answer is yes.
Okay. Oh, perfect.
Simple question.
It can be arbitrary, but yes.
Okay.
So what is the operator?
The operator is the measurement of, God, how do I explain? The operator is applied to a wave function to obtain a certain observable. Okay. Okay.
All right, so our next speaker is James, yes.
Okay, so some principles of wave packet propagation over time, and then some about momentum evolution and the Hamiltonian operators. So, what is a wave packet? It's just a small burst of wave activity that travels as a unit, generally made of a basis of different, it should say sine wave, it does say sine waves, different sine waves that constructively interfere in one area. Now, if we wanted to take this into the context of quantum mechanics, it can be thought of as a packet of eigenfunctions that add together to produce a general wave function. There are two general methods that we've used to track how wave function can change through time. With each, it has its own equation. This first one is the more broad, just general solution to the time-dependent Schrodinger equation. This equation can be changed to fit each scenario, like having a constant potential or having a time constant Hamiltonian. You just drop the integral term and multiply the Hamiltonian by time change. You had that as the case. Now, method two, it basically does the same thing, but with a different mathematical machinery behind it. So first, this part here decomposes the wave function in terms of basis functions. It's a Fourier transform, so we go from position space to a different space. That's basically what Fourier transforms do. They take us between spaces. And the space just means what type of variable we have on our axes, right? So we take a Fourier transform and it takes us to a different space. And in this space, the wave function is deconstructed into a series of different functions here. We've seen this done with plane waves in a Gaussian decomposed into plane waves, but this can be done with theoretically any set of basis functions as long as it can be fit to describe the wave function. Now, as we decomposed it, we take each of those different basis functions, put them in a series, and multiply each basis function by its corresponding energy accruement through time, and then take a sum to add them back together into the wave function that was progressed through time. So this sum isn't an integral like you'd see in a normal inverse Fourier transform, because when we leave coordinate space, we can't always guarantee that the space we're coming back from is going to be a space that can be expressed continuously. So we put a sum there just in case. And that's the inverse Fourier transform part of the Fourier transform part. We change from position, and then we change back into position after we apply the energy. This is an implementation of the code of the evolution of wave function. So to implement wave packet propagation into the code, it must be turned into a discrete problem, since the computer can't, at least not with MATLAB, do continuous problems very well. With the use of a matrix to compose a derivative in terms of finite differences, here, the differential x term is not really a calculus like dx. It's more just a small number, but we chop the whole problem into smaller sections, and we have to divide by that in order to simulate a derivative. So this implementation is able to work for the scenarios we consider the Hamiltonian is not time dependent. So let me go through this a little bit more in depth. So this looks similar to the equation before, except we've got matrices. So we represent our side functions as column vectors that a matrix acts on. Now this is a matrix, this in here, this IH bar over dx is the momentum operator. We just apply it twice, or we could just square the matrix and square the terms, but it does the same thing. as just applying momentum. Because once we turn this matrix over and multiply it by this psi initial over here, it generates a plus term, a minus term, and divides it by a dx for every pair of psi functions down the line. And this matrix is just a diagonal of ones with a diagonal of negative ones set off to the top of it. So now once we apply it twice, we get p squared, and then we divide by 2m to obtain our kinetic energy. But we still need to add potential since it's the Hamiltonian. So we'll add that by multiplying the potential by I matrix, which just has ones along the diagonal, to add that to the Hamiltonian. And then we take this to the power of e. Now, e to the power of a matrix is possible. Normally, you can't just take e to a matrix. That makes no sense. Instead, what we can do is multiply a matrix by itself a bunch of times. So we'll just slap the matrix into the, what is it called? The Taylor series for the e. And what that does is just multiplies it by itself a bunch of times and divides by factorial. We can do that. It approaches a steady value. So we'll take that value, multiply it by this to obtain that. And this is what the code's doing basically. Instead of using calculus, it's using matrices. So we've seen the Hamiltonian normally in class is just the momentum operator twice over 2m plus the potential, the momentum operator negative IH bar derivative over x like before, first slides. This is a little bit different. So this momentum operator has us taking the momentum in momentum space and then using a Fourier transform to take us from momentum space back to position space after we've taken the momentum in there. So we can just get the general equation for taking the momentum operator in position space after we know what we can do in momentum space. So sometimes it's easier to take momentum operators in a different space than it is in coordinate space, and we can take it there easier and then use this transform here. This is basically a 2D Fourier transform that takes it back to position space. And yeah, so this and the matrix, those are the couple of ways we've seen momentum done. And if you want to do Hamiltonian the same way, just do momentum twice, divide by 2m and add in the potential. That's it.
We go back a few slides to the matrix that's in the,
This thing?
yeah, so what is the matrix for?
So this matrix here, so these are columns of psi functions. And this matrix will operate on the psi function to produce a series of finite differences that goes down the column. So here, if we act just the matrix, not any of this other stuff, just this matrix on this function here, it will produce psi of x1 minus psi of x2 over dx times this stuff, like the stuff in the numerator.
So it gets us the derivative with
Yeah.
respect to x.
Yeah, so it basically takes a bunch of derivatives at each of the points that we've split our x-axis into. And we add in these constants and divide by dx because we need to make it look like a derivative. So we do that twice, divide by 2m, and that's basically the same thing as a Hamiltonian. Add in the diagonal elements to be also having potential, and we have a matrix for our Hamiltonian. Now we can take this and raise it to the power v by slapping it into the Taylor series, and that mimics our evolution operator from before. See how the Hamiltonian's in the exponential here? This is basically just a Hamiltonian matrix in an exponential. So, any more questions?
So here you have dx and you have also, or you have dt, right?
Just delta t.
Also
So
okay.
we don't have to have the same time difference every single time, although it may be useful to consider how the system changes in smaller time steps, but it doesn't have to be that way. So I put delta t there just because it can be any time difference that you really want. Within reason, of course. Too far of a time difference in the code kind of generates more errors than you'd like, but
Any more questions? Okay.
There's.
James, that was really good. So you really understand what's going on.
But I just have screenshots.
All right, today I was talking about numeric modeling and quantum dynamics. Under it, we have the modeling quantum dynamics of electron, initial conditions, and alternative methods to compute quantum dynamics. So for modeling quantum dynamics of electron, we can see that modeling quantum dynamics of an electron involves describing the behavior of an electron in a quantum system, which is governed by the principles of quantum mechanics. This wave function, typically denoted as this, is used to represent the quantum state of the electron, and the time-dependent Schrödinger equation is employed to model dynamics. Time-dependent Schrödinger equation can also be written as this, where the first symbol is also known as the imaginary unit, and also we have the reduced Planck's constant, which is divided by 2 pi, and the time which stands for T, and which is the mass of the electron. This is related as the Gaussian operator. It can also be known as the second partial derivative. V is also represented as our potential energy, and this as well is our wave function of the electron. For initial conditions, we can see when modeling the quantum dynamics of an electron, initial conditions are essential to describe the electron state of the state at the beginning of the simulation. One common choice for the initial wave function is the Gaussian wave packet. The Gaussian wave packet is a mathematical function that represents a localized and well-defined position and also a momentum of the electron in accordance with the Heisenberg-Eisenstein principle. So we can see the equation representing an initial Gaussian wave function can be written as that, where we have our wave function in the initial wave function at time t, which is equals to 0. The figure A also is normalized, is also known as a normalized constant, where x is the position of the electron. And we also have the initial position of the Gaussian wave constant. Also, with this representing the width or spread of the wave packets. And the last one, we can say it's the initial wave number, which is related to the momentum of an electron. The alternative methods to compute quantum dynamics for these are actually essential for understanding the behavior of quantum systems. They provide various approaches to solving the time-dependent Schrödinger equation and simulating quantum phenomena. We can also make summary of these methods by using this Schrödinger equation. We can say the time dependence for this equation is represented as this, which some of these functions are already explained in the last slides. Thank you.
Question? James, do you have that? Since it's quite similar to your presentations, right?
I think I get it.
You can look at it.
Yes.
There we go. So If mine's a little wrong, I do apologize. I did my best with this, but I'll try to explain it the best I can. And however, that way you guys can get somewhat of an understanding. So what I have is a discrete representation of wave functions in space, the normalization with the equation of it to help give a discrete representation. And then the size of a simulation cell versus time simulation. So this is the wave function initial conditions here in MATLAB and the code that we had here. So the h bar equal to 1, the mass is 1. Endpoints is 200. The momentum operator is 0.2425. X, the position operator is 40. The variance is 5.5. And these two are those. And this is the wave function here in space and time and the initial. And then this is the normalization of the wave function from the code. This is the wave function is already normalized here, but with the additional square root, it helps ensure that the probability density is equal to 1. So right here is the normalization part of it, and then this is all the other where non-zero velocity of the wave packet is this area. This is the localized part, and that's norm 2. It's a little bit explained in the code there. Here for size simulation versus time simulation, when the wave function, when it starts with momentum, it moves through its simulation, and then once it hits the boundaries in like the graph shown, it will repeat on the end because it kind of gives off an infinite oscillations. So here, as time moves forward, the wave moves from right to left in position. Once it hits the boundaries, the wave repeats itself, allowing infinite oscillations, otherwise known as infinite simulation cells. So it kind of makes like infinite, and it goes and kind of like repeats itself in a circle if you think about it that way. The next thing is just like what happens if like momentum increases. So the velocity increases and the wave moves a lot faster. So what I did, I started with the momentum operator being 1,000. And it went like really fast. It had like 4 oscillations within the time span that we had. So everything else was the same. It was just the momentum operator. It started off, or the momentum value started off as 1,000. So it went a lot faster. And so here in the graph, you can see there was like 2 humps. So it kind of like repeated itself twice. And that's kind of similar to like where it was for 0.2. There's only 1 hump in the, or no, 4, because there was like 2 humps in the picture, but I didn't include that picture, but it's very similar to that one. Where it's 5,000, it's a lot faster. So then the hump's just a lot more steeper, and then, but it moves a lot faster. So it was harder to kind of like, get a good screenshot of it. But yeah, for 0.2, it was a lot slower oscillation. So the velocity is very slow, only 1 hump. And then for where it was 4, there was 3 oscillations within the time span, and there was 2 humps in the mesh, sort of like that. But that is pretty much it. So yeah.
Okay, next.
So what equation are you actually solving for here?
Assuming the normalized one, I guess. I don't know.
Can you go back to your blue figure?
Which one?
The blue one, I guess.
This one?
Yeah, this one.
Yeah.
So I guess you have time, you have position. What is your third axis?
Third axis, I'm assuming is the height of momentum. I'm not too, the height of momentum, but it didn't go from, it went like, I don't know, it was just went really high. I don't know.
Any more question? Yep, Steve.
So you mentioned that it was looping around as a result of the simulation conditions. Can you tell me then what shape it would be if it was moving through like a VO system?
Assuming it would kind of like go down this way, and then it would move back up a little bit. So just like a normal sine graph.
Mm-hmm.
Okay. Here.
So observables. I should kind of clarify, did all the figures and code screenshots in V10HO. So that code we got Wednesday. So it might not be one-to-one with the EAA or whatever the other one. So to begin with, the accumulation of expectation values into an array is pretty much its S3 is the data array, and the accumulation of expectation values is the code that is seen in line 280 mainly, which is the average position. So it's an array of average position, and then AP, and AP is the expectation value. So it's pretty much just an array of the average position and expectation values of position. Sorry, of momentum. And then so the kind of biggest thing from this whole part is saving values into for future reference. So it's just the command is just save -ASCII. And so running this, I saved under a arbitrary variable time and average of S3, which is left out on this slide, but I saved it, and then you can then export that to any graphing software, or in my case, I just opened it in Notepad. You can really open that and work with it in any software of your choice. That's kind of the biggest thing. And so computation of expectation values and momentum, you can kind of see their accumulation is between lines 284 and 290. So it's just and it's the same for momentum, but it's just you just change variables or what you're solving for. And so in PX3 you find where's PX3? Well, that's just a graph of PX3 or I lost where PX3 was actually defined at. My apologies. And so expectation value for energy and uncertainty is pretty much it's just the sum average of everything. Again, of just a bunch of the position and probability distributions of position. And it's the exact same thing for momentum, but obviously just with momentum rather than position. And so, and for energy, E3 and E2 are just the quantum definitions of energy, and E0 is just the classical physics definition. And that should be it.
Okay, thank you. Question?
What meaning of expectation?
It's just the, when you measure something, it's what value you would expect to get, just.
What sort of difference in energy would we find between the quantum energy value and the classical value?
It should be a relatively, if I'm recalling right, when actually finding the numerical value, I believe it was a kind of a 0.1 difference of roughly about that, but you would expect two different values for E3 versus E0.
Sorry, the answer to my question is like expectation value can also be known as average. So it could be used as average of position, average of
One more question. So can you go back to your current figure? Because you show some 3D, yeah. What's the name of this figure?
That would be at PX3, but I think this PX is defined. I think I just forgot to highlight where PX3 was defined, but it would be one of these cases of it's just the accumulation of momentum or position. And I believe Wyatt also touched on what the figure actually is too, because it overlapped.
Okay. Yeah. So for the questions, let's.
Today I'll be talking about visualizing eigenstates as functions and energies for any potential, as well as demonstration of density states for eigenstates. So this is the code for any potential. By manipulating this code, you can change it for whatever potential you need. So this code is mimicking this equation where potential is a function of elongation / contraction of the bond. And so your m is mass and your omega is angular frequency. And so the coefficient in front of your x is actually representative of this mass angular frequency squared over 2. And so you can just put in whatever values you would need for that type of potential and get what you need there. So how changing the potential affects eigenstate energy representation. So this is the code that I used to produce all of these figures and the previously potentials that I also used for doing this. So it can be seen that as you increase the potential, all I did was just change the coefficient. So as you increase the potential, your eigenstate energy differences also change as you get bigger potentials. And it also is seen that the probability distribution under those eigenstates almost flattens out too. So, I mean, it could be probably theorized that if you go to infinite potential, it becomes a constant line. And so this is the density of states, and this is the code that I use for density of states, and it measures from 1 to 15 orbitals. The blue line represents each peak is an eigenstate in the potential that I illustrated as 0.005. So each peak corresponds to a different eigenstate at the discrete energy level. The red line indicates the density of states as you move farther away, so higher energy. And it gets to a point where it starts to tail off, and this tailing off is indicative of when the two things dissociate from each other. So it's the dissociation energy of your system. And that's it.
The question?
The potential, as you increase the energy, it's just the distance it oscillates that increases, not the frequency stays the same, right?
I'm not sure.
What is your energy as a ground state?
Energy for ground state?
Yeah.
Zero. There's no energy.
So you mean the ground state for the electron state is 0? You go back to your figure.
Yeah. Yeah.
So what is your y-axis? It's energy, right?
Yeah.
What is the position of your ground state?
Position?
Yeah.
Somewhere.
What is the value? Yes.
Somewhere in between.
It's not 0, right? More question? Send our speaker again. Speaker.
So we're going into 2D. So the understanding of this depends heavily on what James presented on, that matrix that was in the exponent. That's what we're focusing on right now. So what's the big deal? Why is going into 2D a problem? So we saw that a 1D wave function required a, and I apologize, it should be 2D operator, not 2 by 2. So 2D and a psi vector in that exponent that James showed. But why did it require that? So just as a reminder, we have a wave function in one dimension, and we want to know how it's changing with respect to x. So we can slap it in that exponent and kind of mimic the Hamiltonian to get the evolution operator. So why are we doing it as a matrix? So continuous kind of sucks in MATLAB. Computers aren't very great at doing continuous processes and going to infinity. So we want to discretize it. We want to make it discrete. So we're going to have a psi value at each point. And obviously you can decrease the distance between those points, but this is the basic fundamental understanding. So what we're going to do is we're just going to take those psi values, flip them on their side and slap them in a vector. And we're going to multiply it by an operator that would calculate the difference with respect to x. So how do we make it 2D? So same difference, or same thing, but a little bit different because we have a whole table of psi values now. And again, this should be a 4D operator and a 2D vector, since we have a two-dimensional, I guess, table. That's how you can see it. And that's kind of gross, so we're not going to do that. We're going to make it easier. So what Dimitri was kind of commenting on in lab on Wednesday was how we could turn that huge table of psi values into one vector. So we're going to take all the columns essentially of this matrix and stack them on top of each other into one vector. The problem here is what Dimitri was trying to go over on Wednesday is how we convert the indices of this matrix into the indices of that one, because this one would be labeled 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, and this one would be 1, 2, 3, 4, 5, 6. So the code is really implementing that conversion there. And this is just for the psi vector. This is borrowed from an undergrad from 2 years ago, Sibel. But she talks about the Hamiltonian up there, but what I really wanted to point out was how that index is calculated for converting those vectors, those psi vectors. I'm not going to go into the math to show how it works, but essentially this would convert our matrix indices into that single dimension vector index. And then we want to turn that, again, 4D operator into the 2D operator. So essentially we're going to have our two operators for each dimension, as well as their degrees of freedom. And we're going to multiply them and sum them. And that gets us our super operator. I don't completely understand the math here, but Dimitri asked me to show it. So this is how it's implemented in the code. So we can see we're iterating over that whole table. You can imagine I as that the index in the x direction and j is the index in the y direction, or vice versa. And we're calculating a big index, which is just the index for those values in the psi, the one-dimensional psi vector. And we're calculating using the indices, the two-dimensional vector. Yeah. And so here is an example borrowed from Ava's project from last year. This is a potential surface that she has shown here in 2D. And then here are some snapshots of different eigenstates with their associated energy values on a two-dimensional potential surface. Yeah. That's it.
What the colors indicate on these figures.
The colors would be. It's a really good question. So if we could see these at an angle, the warm colors would kind of form hills, while the darker colors would form cavities. I believe that they'd be the wave functions at those points. I don't think they'd be probability, because I don't think you
Is
have,
this wave function or potential?
this is the wave function on that potential surface.
Okay. So the colors represent height here.
Yeah, no. I don't know what the height is of though.
What's the meaning of the negative energy?
I'm not sure.
More question? Second speaker again.
Okay, so I will be talking about visualization of the different, for different wave packets. Okay, so first, real and imaginary parts. As you see on the left side of the screen, that's just the real part of the wave packet. And then on the right side, it's the real and imaginary. And in the code, you can see this is by first plotting the real, and then folding, and then plotting the imaginary. And then the last one is us doing it times 3. And if we switch it, we can see it's 3-dimensional. And that spiral is because it's showing that there is both imaginary and real parts of the wave packet. Okay, potential and probability distribution. So first, this is just plotting our potential. And then this kind of shows how both these graphs are similar, because this first one is just the probability, and then the second one is actually the absolute value of the psi function and that whole value squared, and it shows that those would give you the same graph and answer. Okay, why are there 3 of them? This is because we have multiple different methods. So we have the first 2 methods, the last 2 methods, which is method 2 and method 3. And those are our preferred methods. The first method we don't use very often because it's about propagation in the momentum space, and it's only relevant in free space. And we as humans don't like talking about things that aren't really there. This code kind of helps bring us the 3 different methods. And this is just showing the near past and going into the near future. And then this is just an example in the code of where this 3rd method happens that we don't use very often. Visualization of observables. So we had the 3 different observables. So we had the expectation value of position, and then the expectation of momentum, and the expectation of the others. And then this is shown by the expectation value is the average, the accumulating averages and values. And we use this by the AVGS and the AVE to calculate the averages in the code. And one example of this is where we take the average sum of the probability. And this one instance is instantaneous, and it's only showing 1 point at time t. But we would like to be able to plot it, we need to put it in brackets, because that will allow it to plot more and more points of the different averages at the average at different times. The organization of data and bundling groups of observables. So it's really helpful in research to see all of the observables at one time in one figure. And if you do this by doing multiple subplots, and this is shown by the 311 would be the top, the 312 would be the middle, and the 313 would be the last of the figures. Yes.
A question from audience?
I go back a couple slides.
Yeah.
This one
What's
works.
this one? Okay.
What does the period star indicate in your equation?
Period star, good question.
The element wise multiplication.
Oh,
You go to the next slide. So here you have dashed line and you have solid line, and you have blue and you have red. So what are those?
so I believe the dash line is what like would be our expectation of like what we would think that it is. And then I believe the red line, the difference between the red and the blue line is the different methods we used. And that's what the actual, what is it? Actual probability of it happening if by running the code and like the actual values, where the dash line again is like what we would expect it to do if it was like perfect.
All right, I'll be doing summarizing quantum dynamics as movies. So to start off, we want to do what we did before, where you want to define that you want to make the movie and then put the title, and then you want to open the file before the loop starts. And then in the loop, you want to put the get frame and then write video so that it collects different frames for each iteration of the loop and then collects it to the video. And then after the loop, you want to make sure that you close the video. And then once you do that, you can do what we did before, like where after you run the code, it will generate the video file, which you can either upload directly to YouTube or you can import it to a video file, and then you can use a video player to watch it that way. So when you go and make the video,
Speak to stop the drawing.
if it was a video, how do I play it? Because it was a video file. All right, so here's the video. And that's just using the standard parameters for the code. So then if you want to change some of the parameters, you can go to like line 64 for the potential. If you wanted to make any changes to potential of your system, you can do that there. And then if you want to change the initial position and momentum, you can go to line 6 and 7 and change it there. And then you can get the different videos for the changes you made. And then here is an example of changing the initial potential. I changed it from like a square to a cube. It looks a lot different than before. And then I did another example where I changed the initial momentum. And you can tell it's not moving. That's why. It doesn't move quite as much as originally, and it doesn't go as far and doesn't move as fast as originally. But yeah. Yes.
Can you go to your topic?
Go to what?
Your topic. Your topic, the first slide. Can you explain what's quantum dynamics?
Quantum dynamics is like how like a particle behaves in its environment, like with the initial position, momentum, how that particle interacts in that environment.
Can you go to your illustration, like of the potential energy surface?
Yeah.
So what is moving? When you play your moving, what is moving? What's that Gaussian shape that's?
That is the wave function.
What's your x-axis?
That is the position.
And your y-axis
is the y-axis is the can't remember what the y-axis is. Probability. Interesting. So as the thing moves, probability changes, I think. Okay.
If your y-axis is probability, then how can you put your potential energy? How can you put your potential into this figure?
The potential. I think it's represented by the green line, I believe. But I don't know how it actually goes into the figure itself. The potential energy or the curve just shows that it oscillates inside the potential. The potential like isn't placed there to properly show like, oh wow, this is the potential. It's just the curve oscillates inside the potential, and that's the point of putting it there.
Slide.
Yeah.
So right at the top, you have the S3 equals whatever. What does the apostrophe mean in that equation?
Transpose. Yeah, transpose. No? Well, transpose.
Complex conjugate transpose.
Okay.
Period. Apostrophe would just be transpose.
Good to know.
Okay, no further question. That's second speaker. So let's invite Dr. Kyden for concluding remarks.
Thank you, Dr. Han, leading the discussion and substituting. I will watch and see how do you perform and ask the visitors, but I hope it went very well based on what I've heard. Many thanks for doing it, and I believe this will set up a foundation for a research project, unless you select to do a written exam instead. So unfortunately, there are two homeworks, one based on questions on this stuff, and then calculus-based calculations for Wednesday, but hope you will overcome it easily. So I thank all speakers and chair of today's session and visitors. And as a favor to me, please symbolize the end of the meeting. Okay, so meeting is dismissed. Everyone is welcome to depart, disconnect, and go forward to Monday.
Wow.